Alright, let's talk about organic chemistry. Everything you're going to learn at the college level, at least for the first class. First, you're going to start out with some alkane nomenclature. So let's go ahead and draw an alkane. That's 11 carbon atoms. Let's add a substituent, a bromine, to carbon number 3. How do we know that's carbon number 3? Well, we got to number our parent chain, starting at the side to which the substituent is the closest. So since the bromine is at carbon number 3 and there are 11 carbon atoms, that makes this 3-bromo-undecane. Let's add some more substituents and make this a little more tricky. As you can see, there are 3 methyl groups. That there in the blue is an isobutyl group. We got a chlorine at carbon 8 and a bromine at carbon 3. So we write all this down and then we put it all together in alphabetical order. That gives us 3-bromo, 8-chloro, 5-isobutyl, 2,2,9-trimethyl-undecane. Let's talk about R and S. So let's start with pentane. We're going to add a chiral center to pentane. That's the same as an asymmetrical carbon atom, not to be confused with a stereocenter. So we'll add a bromine to carbon 2. We'll put our hydrogen in the back since it's the smallest, and I'll explain that shortly. And we'll put a chlorine up front. Everybody knows chlorine's green, so we're going to make it green. I should have made the bromine purple. There we go. Alright, so now we have 4 different substituents on carbon number 3. The bromine is in the 2 position, the chlorine is at carbon number 3, and the parent chain is pentane. So what is the difference between an asymmetric or chiral carbon and a stereocenter? Well, an asymmetric or chiral carbon has 4 different substituents attached to it. A stereocenter means that if you change any of the substituents, it will yield a stereoisomer. So let's number our substituents on carbon number 3. Chlorine is the highest priority, followed by the carbon chain, which has a bromine attached to it, followed by the ethyl group, numbered number 3, and then followed by the hydrogen, number 4. So they pretty much go from heaviest to lightest. And then if you need to review the rules on this or look them up, check your book, because I don't have time. So when your numbers go counterclockwise, it's S configuration. So this would actually be 3S, 2-bromo-3-chloropentane. Alright, so alkene nomenclature. The double bond is going to take priority. So let's look at heptane. Put a double bond at carbon number 3. Now that's no longer heptane. Change that A to an E. Double bonds at carbon number 3. That gives us 3-heptene. Google it. Let's add a bromine at carbon number 5. Notice that the double bond takes priority when you name your parent chain. Let's talk about E and Z isomers, because these are specific to alkenes. So when I think about Z, I think about Onzizamzide, right? Because E, you can't really do that with E. So let's look at this molecule. If we split that double bond, that's what that orange line is, that squiggly orange line. We number our substituents in order of priority, pretty much weight-wise. You know, you want to think about what weighs the most. It's simple. Okay, so the ethyl weighs more than the methyl, so you're going to number that number 1, and you're going to notice that it's on the same side as the oxygen, and that's going to be your Z isomer. So let's talk about alkyne nomenclature. That rectangular block in the middle is supposed to be a triple bond. We have a methyl group and an ethyl group attached to acetylene. That gives us ethyl-methyl-acetylene. Pretty simple stuff. You're not really going to have to worry about that too much. Now let's talk about alcohols. That's phenol. Phenol is resonance stabilized. So that means that those electrons can travel around that molecule. The conjugate base is very stable. It can be deprotonated with sodium hydroxide. That's very important because other secondary alcohols can't be deprotonated with sodium hydroxide. Only resonance stabilized alcohols such as phenol, where the pKa is about 10. Primary alcohols can only be deprotonated with sodium metal or sodium hydride because its pKa is a lot higher. It's about 16. So that proton wants to stay attached to that molecule. Okay, you need to know what your positions are on different molecules. Benzylic, phenylic, allylic. I'm not going to go through that because you can look that up on your own. Resonance is huge here. These positions display resonance and make those positions on those molecules stable, and they make your radicals and stuff move around and carbocations. I'm going to design a chart to go through SN1, SN2, E1, and E2. And if you memorize this chart, you're going to have a really easy time in this class. I would draw this chart over and over and over and over again, because when it starts to become second nature for you, you start to memorize all of the reasons why these reactions happen the way they do. So you want to look at the substrate, you want to look at your nucleophile, that's Nu. You want to think about stereochemistry, that's Sc. You want to look at your reaction coordinate, that's the graph of energy versus the progress of the reaction. You want to look at your solvent that you're going to use. Are there rearrangements? What other special things happen? So in an SN1 reaction, you always use a tertiary substrate or a secondary substrate, but it prefers tertiary substrates. SN1, E1, and E2 all prefer tertiary substrates over secondary or primary substrates. SN2 is the only reaction that uses a primary substrate. First order reactions use weak nucleophiles. SN2 and E2, second order reactions, use strong nucleophiles. But E2 is specific in that it wants to use a strong base. So OH- or RO-. SN1s proceed with racemic stereochemistry. SN2 proceeds with inversion. First order elimination usually goes with the most substituted elimination, and E2 always goes with an anti-coplanar elimination. And you get Zaitsev or Hoffman products depending on what type of base you use, whether it's bulky or not. So in your reaction coordinate for first order reactions, you're going to have two peaks because you're going to have carbocation intermediates. For second order reactions, you're only going to have one peak because you only have one transition state. First order reactions prefer polar protic solvents like water. SN2 prefers acetone. So whenever you see acetone on a reaction question, you can automatically just about assume that it's going to be an SN2 reaction. E2s prefer alcohols specific to the shape of the base you use. Rearrangements only occur in first order reactions, never in second order reactions. If you ever see silver nitrate on a reaction arrow, you can pretty much assume it's going to be a SN1 reaction. So let's talk about SN1 reactions. Remember, they use tertiary substrates. The first step in an SN1 reaction is the kicking out of the leaving group, which in this case is going to be a bromide ion. So we have our solvent, methanol. The bromine is going to get kicked off by heat or some other sort of electromagnetic radiation, generating a carbocation at the tertiary position, which is very stable, and a bromide anion. The electrons of the oxygen on our methanol are going to attack that carbocation, and they're going to attach to it and form a new bond between the oxygen and the carbon. The positive charge is going to switch from the carbocation to the oxygen. Another molecule of our methanol solvent is going to come in, and it's going to abstract the proton from our newly formed ether. And the electrons which connect the proton to the oxygen will be given to the positively charged oxygen because oxygen is an electronegative atom. Our methanol now takes on the positive charge and forms a salt with the bromide anion. Our protonated methanol forms a salt with the bromide anion. So now we've formed an ether and a salt. This is your basic SN1 reaction. SN2 reactions. These are really important. They're very abundant in organic chemistry. You're going to see a lot of these. Okay, so we're going to start with a primary substrate because that's what SN2 reactions prefer, and a good nucleophile, OH-. We're just going to throw these hoes around everywhere because they're all over the place. They're solvating this bromomethane. And as you can see, the bromine, being very electronegative, abstracts some of the electrons from that central carbon, making it slightly positive. Our base, which is negatively charged, then wants to attack that slightly positive carbon, and the bromine wants to take those electrons from that carbon. These hydrogens out here, you could substitute these with different groups to realize how the stereochemistry of this works a little bit better, but they shift to the right because that OH wants to take on that new position as that bromine leaves. This here is a transition state. It's denoted by putting brackets around your molecule and putting this little funky looking T thing up in the corner. As you can see, the transition state is planar. And as the hydroxyl group attacks, it shifts those hydrogens to the right and kicks that bromine out. That is called stereochemical inversion, and it is specific to the SN2 reaction.